Welcome to my channel and welcome to my office and welcome to you, Manuel Meyer,
Thank you.
my colleague here at STU.
Exactly.
Yeah. So you've been here how long?
I've started at STU 1st of January 2023, so that makes it 3 years now.
So you've done a lot of things in 3 years, and before, of course. Actually, you're doing quite a lot of different things when I look at it from my
Yes.
perspective.
Yeah.
You're doing basically things that are cosmology, galaxies,
Right.
dark matter,
Exactly.
particles.
Yeah.
You're doing observations and
Also
experiments
that.
also.
Yes.
So a lot of
Exactly.
stuff.
Yes.
But what are you up to right now? What are you doing right
Yeah.
now?
Yeah. Exactly. So as you say, I'm involved in quite a lot of things, which is a little bit because of my background. I come from more the astronomy, astrophysics side, or as we call it, astroparticle. So trying to understand what we see in our galaxy and other galaxies using particle physics. That's where I'm coming from. That's or the field in which I did my PhD. And I was always fascinated by discovering or looking into the most fundamental constituents of our universe. And I'm trying to decipher what dark matter is. So we know that there's this mysterious substance that we call dark matter that is much more abundant than the matter that we are all made of. And our best guess right now is that dark matter is made up of one or several new fundamental particles, and we're trying to find traces of these particles, either by looking at the sky using telescopes and finding traces of this dark matter, or by looking at it or looking for it directly in our laboratories, because dark matter should surround us also here in our solar system, and hopefully also be inside our laboratories and hit our detector from time to time.
Yeah. So basically, I mean, you're sort of a typical astrophysicist in the sense that you care about the entire universe from the smallest thing, if you can even talk about scales, and then the largest thing,
Exactly.
namely the universe, development of
Yes.
the universe,
Yeah.
and trying to connect these things.
Exactly. And this is also why I really like astroparticle physics in general, because you have to connect these, our sort of fundamental constituents of nature, our elementary particles and how they interact. And you have to connect that with astrophysical environments. What happens in the vicinity of black holes or in the remnants of supernova explosions, so sort of the most violent environments that we have in our universe. And if you want to explain what we see with our telescopes, you need to invoke particle physics. So this is always what fascinated me. But lately, I've transitioned more into the laboratory, thanks to a research grant that I got from the European Research Council. I have been able to amp up my experimental side of things. And right now, we're developing very sensitive detectors that can detect single photons, so single light particles, very efficiently with low background rates, which is exactly what we need for certain type of theories that predict or that predict what dark matter could be.
Yeah. And speaking of that, looking at your papers, it seems that you may have a favorite.
Yeah, I do. I do. I cannot deny it.
What's your favorite particle?
Yeah, okay. So it's called the Axion. It was predicted or invoked in the late 70s to explain something that is unrelated to dark matter, something that we call the strong CP problem. So essentially, in the interactions that hold together nuclei, and if you write down that theory, there's a little problem, and that problem you should be able to observe.
Very persistent problem.
It is a very persistent problem. It's essentially a fine-tuning problem. There is, if you write down the theory, there's a term that should be of the order of 1, but it turns out from experiment that it has to be smaller than 10 to the minus 10, so 0.0000, 10 zeros and then a 1. And if you want to explain that naturally, then people usually invoke the Axion. And then it was quickly realized that this is also a very good dark matter candidate. And for some reason, during my PhD, I got drawn into Axion physics, and I kind of never left it.
A PhD can do that.
A PhD can do that, exactly.
So you've been working both with observations and experiments, theories.
Yes.
So what's your view on these things coming together? Because many people only do one of these.
Yes. So I always tried during my career to at least get a fair bit of understanding of the theory. because I think it helps you also to, if you want to design an experiment. Of course, there are theorists who do nothing else, and sometimes, or it often makes sense to talk to these people to get ideas or exchange ideas, bounce around ideas, and also to, in order to design a more sensitive experiment to search for these particles. But I think it still makes sense to have this background. It's also what I try to tell my students, not just write down the equations, but a little bit of an understanding where they're coming from. It's also more fun. To be honest, not just to learn something by heart, but to have an idea where these things are coming from.
What's the physics of this?
Exactly.
So what's the physics of that you wrote on the backboard?
Then I wrote on the backboard here. That's actually the interaction, or one of the interactions that this axiom might have. So hopefully it interacts a little bit with the particles that we know, like light.
That would help.
That would actually help. Otherwise, it's very hard to detect these things. But one of the cool things about this interaction is that we might be able to produce these axions if we just shoot light into a magnetic field. And with that, we might actually be able to shine light through walls, which is kind of a crazy idea. But the idea would be, okay, you take a strong laser, you shoot it through a magnetic field. In that magnetic field, some of the photons, some of the light particles of that laser turn into axions. They go past some opaque barrier that doesn't let any photons through. And then on the other side of the wall, you put another magnet, and then these axions convert back into light. And this light you could detect. So this is why, and okay, you can imagine that this is not happening all the time, otherwise we would have already seen it. So you need very sensitive light detectors. And this is one thing that I'm working with.
Magnetic fields are, I mean, close to my heart. And sometimes for some physicists, it's like you invoke a magical thing. Magnetic fields are kind of a magical thing. You would rather either avoid them, or you use them only if they can help you to explain something. And in this case, it helps.
It does help.
You don't put B equals 0.
Exactly. But it's a huge playing field. You can look for the same process in astrophysical observations, and then you need to use astrophysical magnetic fields, which we believe are everywhere essentially. But they're then quite hard to model because, okay, we of course know a fair bit about magnetic fields in our universe, but it's very hard to precisely know where this magnetic field is pointing to and how strong it is in different environments in astrophysics. So that also makes it fun because it can be a little bit creative. You have to comb through the literature and see, okay, what is the magnetic field, for example, in a cluster of galaxies? In between galaxies, there's gas that also harbors a magnetic field. And then you try to model that in some way. So this is also sort of a creative process. And then
that is why magnetohydrodynamics is so important.
It is.
How do you generate magnetic fields and how do you sustain them?
Exactly.
Dynamos and so on.
Exactly. So, it's very important, and it's.
I'm glad you're considering magnetic fields.
Yes, you're welcome.
Anyway, so you're doing all these different things. So it's natural to ask. So what's next?
So one thing that we want to do is actually look for dark matter in the basement of our university. So we're building a little dark matter detector.
Not just in the basement of the universe, but actually in the university.
Yes, exactly. So it will be a little prototype detector where we essentially put 2 mirrors inside a magnetic field. And these mirrors are just placed in the right distance from each other so that you get a resonant enhancement of the little electromagnetic wave that should be formed if the axion interacts with the magnetic field. So if you place these mirrors in the right distance from each other, you will enhance the electromagnetic field with a certain frequency. It's similar to how an organ pipe works, essentially. And this signal we will try to measure. So this is something we wrote in a paper last year about the sensitivity of such a device, and now we actually want to build it. So this is one thing that I'm pretty excited about. Then we're also getting a new PhD student that will help us with our single photon detectors to further bring down the background so that we can see maybe the light that passes through the wall. But these detectors have a broad range of applications. So I think that will be interesting also in terms of quantum communication. Also, these detectors are used for what we call bosonic quantum computing. So yeah, I'm pretty excited about that and see for what else we can use these detectors in the future.
All right. Well, that's I mean, a long future ahead of you, I think.
I think so. I hope so.
So one thing that I just thought I might ask you is these actions, if they are really there, and they interact, with maybe magnetic fields indirectly and produce. So where are they in the universe? So because I think some dark matter candidates would then, some might tend to accumulate in various ways. Some even say in the core of the Earth or in celestial bodies and so on. So what about these ones? Where would you find them?
Yeah, so typically, and this goes for axions, but also for other dark matter particle candidates, usually we would expect them to clump at the center of galaxies. So usually they form halos around galaxies, but the highest concentration you usually find in the centers of galaxies, and then also in centers of galaxy clusters. So whenever you have essentially big masses in the universe, because dark matter actually acts as a potential well that sucks in all the other matter, and we need it in order to form our galaxies. So we wouldn't be here without dark matter, actually.
But how many actions would you need in this room, for instance? But because we know that neutrinos, they just go through everything and through the palm of our hands.
Exactly.
A ton of neutrinos every second going through. So what about in here?
Yeah. So for the detector that we're building in the basement, it depends a little bit on the mass. So these axions, they're especially because they're predicted to be very light in comparison to other dark matter candidates. So they would be kind of the lightest particle that we would have discovered so far. So the axions that we're looking for in the basement, they would be pretty numerous. So each cubic centimeter should hold around 1 trillion of those. So a lot.
No more, no less.
Yeah, no more, no less, exactly. But they interact so rarely that it's still very hard to find them.
So in that respect, they are similar to neutrinos.
Exactly. Yeah. But neutrinos are, of course, they are very fast, almost at the speed of light. So they actually inhibit structure formation. We need cold dark matter, as we say. That helps for the clumping for all of the structures that we see. So we need this cold dark matter.
Well, for one, I'm looking forward to learn if you actually detect them in the basement.
That would, of course, be the most fantastic thing.
A fantastic discovery.
That would be fantastic. Yes.
So, but maybe on what timescale are we talking about here?
Well, we're just setting up the experiment now, buying the first components, essentially the electronics. We have friends in Tenerife who are experts in machining mirrors precisely at these at the frequencies that we're looking at. So until we maybe get the first prototype, hopefully next year, I would say.
All right.
And then starting measurements, maybe serious measurements, maybe next year. That would be great. But then this will not be at the perfect sensitivity. If we want to really drill deep into this unknown parameter space, this will take multiple years. And depends on funding, of course.
I think a year, I can live with a year.
Right? Yeah. We might be able to, look for particles where nobody has looked before within a year. If all goes well, but usually in experimental physics, this is what I've learned now, it usually takes much longer.
But a year is a good horizon, and I think that to boldly go when no one has gone before is really a perfect place to end this conversation. And then maybe we should check in again with you in a year and see how you're doing.
Yes, I would love that.
All right.
Thank you,
Well, thank you for coming.
Thank you very much.
Thank you. Bye-bye.
Bye.